Welcome to Microbial Insights Ask a Scientist series, where people like you submit the questions to us, and Sam and I will try to answer these. I'm Dora Taggart, CEO here at Microbial Insights.
And I'm Dr. Sam Rosolina. I'm Vice President of Applied Innovation at Microbial Insights, and this is our second video in the series. And just as a quick recap, our previous question was on where we are currently in the world of petroleum hydrocarbon degradation. And so now we have a new question that I'm very excited about. And that question is, how do microbes work in mixed contaminant plumes?
That's a really great question, Sam, and I think it's one that really illustrates the importance of understanding microbes and bioremediation. So first of all, let's talk about what we mean when we say a mixed plume. So when you have parent compounds like tetrachloroethene or PCE that are present at sites, they'll form daughter products like TCE and cis. I don't consider that a mixed plume because that's the parent and the daughter, same degradation pathways that we're looking for, right? But when we think about different classes of compounds, like when we're talking about chlorinated compounds or petroleum hydrocarbons, those would be what I would consider like a commingled mixed plume, or even chlorinateds and 1,4-dioxane.
Right, yeah, that makes sense. And last time, in the last video, you mentioned that these microbes, when we're talking about biodegradation, we want to make sure that they have everything that they need. So that is just like us. They need food to drink, they need something to breathe, food to eat, something to breathe, nutrients, and that's really important for us to monitor here, right? So oftentimes we talk about electron acceptors and electron donors in the remediation industry, and those are really important topics when it comes to biodegradation. When we're talking about electron donors, we're talking about compounds that give these microbes electrons, and they also provide energy or food for those microbes. When we're talking about electron acceptors, it's something that these microbes are using to respire in the same way that you and I use oxygen to respire. And it's really important to have both of those for the microbes that are present, because what it does is it completes that chain reaction of electrons, and those electrons kind of power everything that's happening within these microbes, all of these different processes. So we want to make sure that we have both of those present. And when we talk about electron acceptors, these are pretty common in the industry to think of in terms of the redox ladder. And so we'll show that on the screen now, but when we're talking about the redox ladder, we're often saying, what are the electron acceptors that are involved? And so you can look on the left side of this screen and you can see that there are electron acceptors as well as reduction products on the right-hand side. On the left-hand side, you see those measurable redox indicators. And so when we're talking about the redox ladder, we're talking about starting with something like oxygen, which is a super high energy source. A lot of organisms can use it really rapidly. But when that depletes, then we look at microbes that turn towards other electron acceptors, like nitrate, and then when nitrate is depleted, we turn to manganese, and then to iron and sulfate, and finally to methanogenesis. And so these check marks that you see on the screen, these are indicative of what compounds can be measured to tell us what redox conditions are present at the site. And so when it comes to mixed contaminant plumes, we see that not only can the electron acceptors on the screen be used, but also things like chlorinated ethenes can be used for certain organisms. And when we're talking about halorespirers, that's what they do. They respire these compounds like chlorinated ethenes and ethanes, and they degrade them in doing so.
Cool. And meanwhile, when you have a commingled plume, compounds or contaminants that are present like petroleum hydrocarbons can be BTEX, naphthalene, larger PAHs, or even straight chain alkanes. These compounds are electron donors, so they're the food source for the microbes. And so when you have a lot of these compounds that get introduced into that subsurface, you rapidly have a lot of food that's available. So everybody gets excited that can use it, and so they start to consume these products and break down the BTEX and utilize those compounds. But in doing that, they're using all those electron acceptors that are available. So your oxygen's gone, your nitrate's gone. We're going to show you a picture here, and you can see the plume becomes depleted very, very quickly, so that source area rapidly changes.
Right, and that's why it's really important to monitor in situations like mixed contaminant plumes, right?
Exactly.
Because when we're looking at halo respirers, when we're looking at reductive dechlorination, that happens best right between sulfate reduction and methanogenesis. So we want to know that we've hit that sweet spot without kind of overdoing it. If we overshoot it, then we have methanogens that are kind of outcompeting these organisms like Dihalococoides.
Yeah, that's right. So with commingled plumes, there's like this tension that occurs in the site, and petroleum hydrocarbons will help us create this reduced condition that Sam was talking about, but you want to be sure you don't get too reduced, and we get into that really dramatic phase of methanogenesis where you have a lot of methane that's being produced, and so we have a lot of other concerns that can come into play, like vapor intrusion or things that can occur during those situations. So really we want to be sure that we're looking at all of these factors as we take into account what's going on there.
Right, yeah, and another concern that's involved in mixed contaminant plumes are non-aqueous phase liquids. Yep. And that's when the concentration of these compounds are so high that they're not even soluble in the water. And so petroleum hydrocarbons are light non-aqueous phase liquids, or LNAPL, and these kind of hang out at the surface of the groundwater, and they kind of move along when the groundwater goes up and down, and so they spread vertically. Yep. And when that happens, they can actually impact some of the permeability that's occurring in the subsurface. And then TCE, or chlorinated ethenes, are DNAPL, or dense non-aqueous phase liquid, because they're more dense than water. And so they hang out down at the bottom, and they can cause problems in terms of falling into fractured bedrock and things like that. But they can also, the LNAPL can enhance the absorption of TCE, and that can make it difficult to understand what compounds are actually present. It can mask some of that DNAPL.
Yep, definitely. And then like Sam was saying, this DNAPL is in those deep zones that are really hard to penetrate. So getting down in and adding your electron donors that you might need to be able to get the remediation of that DNAPL can be really difficult. And it can, create, as I mentioned before, methane. And so you have all of these gases that are coming to the surface. You're creating vapor intrusion risks. And so how do we do this effectively? So to be really good managers of the tools that we have in environmental remediation, we want to look at the chemistry, we want to look at the geochemistry, and we want to look at the microbes. Take that multiple lines of evidence approach to get good monitoring practices that are in place. And by having these, especially when you're talking about commingled plumes, that increases that degree of difficulty, you really want to be able to do that, because that's where you get precision bioremediation that can occur.
Yeah, that's exactly right. So we always want to take that multiple lines of evidence approach. Really understanding the biogeochemistry is just as important as understanding kind of the contaminant bulk concentrations and amount that's present. And so monitoring those are really crucial. And then in terms of that microbial portion, using Quanare chlor and Quanare petro in conjunction with one another gives you a lot of information about the pathways that are present and what you can do at this site to kind of enhance that or make sure that those conditions are appropriate. So we talked about kind of a very obvious mixed contaminant plume, which is not to say that it's not common. It's very common to see petroleum hydrocarbons and chlorinated solvents together. But what about other mixed contaminant plumes? I mean, we're talking about like chlorinated solvents and heavy metals, or 1,4-dioxane, as you mentioned, and chlorinated solvents. What about these kinds of mixed contaminant plumes?
And let's complicate it even more. What if you have landfill leachate that's been introduced into this plume, and so now you've got all these methanogenic conditions. So, like Sam just said, this is pretty endless, the amount of combinations that you can have. The good thing is, Microbial Insights has been doing this type of analysis for over 3 decades. And so when you take all the experiences that Sam and I have and the other staff that we have here at Microbial Insights, and we put them into play, we've likely seen some part of this combination at some point during our careers. So what we love to do, and we've mentioned this in other videos, and if you've met us at conferences, we love to talk with you, to exchange ideas, to have you ask us questions. So call us, tell us what contaminants are there, tell us what your questions are, and we can really help you design the best approach as you're moving forward, whether it's here's the study I'm setting up, Sam, and I want to know, I've got, chlorinateds and petroleum hydrocarbons, and if I'm looking at my plume, where should I pick the wells?
Right.
Because if you don't start the study right, it's not going to answer the questions that you intend to. So reach out. We can help you in the beginning of the study. We can help you with data interpretation, and I think Sam will agree that's the best part of what we do every day. So happy to have your questions. Email us at info@microbe.com. Reach out. We'd love to talk to you more.
Yeah, absolutely. And that's really built into the service that we provide. And I think that's really important for people to understand that that's part of the process. So yeah, as Dora said, thanks for joining us. If you have questions, reach out to info@microbe.com. And also, if you have a question to submit for Ask a Scientist, please submit it at info@microbe.com as well. We're really excited about this. We've gotten great feedback on the first video of this series, and we're excited to keep going. So please tune in, and we'll see you next time.
Yeah, love to hear from you soon. Thanks.